In the previous lesson, we saw that, as powerful as it is, relying on the relative frequencies of single characters in a piece of ciphertext that we know or suspect was encrypted using a monoalphabetic cipher often isn't sufficient to really break open a cipher system. But even so, this tool alone reduces the computational security of such a cipher enormously. Recall that a brute force attack against an English cipher would require on the order of 10 to the 26th key trials. Let's assume, somewhat optimistically, that our use of single character frequencies lets us correctly group the ciphertext characters into the most frequently used 9, the least frequently used 9, and the remaining 8 in the middle. From there we decide to brute force all of the resulting combinations. For a set of 8 characters, there are 8 factorial, or 40,320, permutations, and for 9 there are 362,880. The number of keys we would have to try is 9 factorial times 8 factorial times 9 factorial, which is about 5 times 10 to the 15th. Definitely still a huge number, but for every key that we have to examine, we have eliminated about 10 to the 11th or 100 billion keys that we don't. This, all by itself, is an enormous break in the security. In practice, it is even far worse than that, or better, depending on if you're Alice or Eve, since not all of these keys are equally likely. The very first key we try, the one that is simply the order of the expected frequencies, has a fair chance of revealing enough correct mappings that an experienced cryptanalyst can start spotting partial word matches which will guide their efforts on which mappings to choose next. Even if that's not the case, as they proceed down the list of slightly less likely mappings, they will very likely soon come to one that breaks things wide open. The analysis of the effective security of a monoalphabetic cipher in the face of different types of frequency analysis would be interesting to see, but I've been unable to find any references to where this has been done, though I'd be very surprised if it hasn't. But with the limited resources and limited ciphertext to work from, it is also quite possible that this reduction in key space will be nowhere near enough to allow us to succeed in a useful amount of time. So let's accept, for argument's sake, that we probably can't just map the single letter frequencies to determine the mapping. What other tools are at our disposal? Quite a few, in fact. Remember, anything that is recognizably non-random can be helpful. Instead of looking at single letters in isolation, we can look at how they appear in relation to other characters. We can analyze sequences of any length we desire, but the number of possible combinations increases quickly. For example, there are 26 squared possible digraphs, or 2-letter sequences. This is only 676, but there are over 17,000 possible 3-letter trigraphs and nearly 500,000 possible 4-letter combinations. In order to be useful, we really need a given sequence to appear more than once. At least 3 times would be nice. Keeping in mind that we would typically only have a few hundred, or if lucky, a few thousand ciphertext characters to work with, we would only be able to focus on the small handful that would be expected to occur at least a few times in such a small sample set. For a 250 character ciphertext, this means sequences whose rates are at least about 1%. More often than not, such repeats are probably common words or common roots, prefixes, or suffixes of words. For instance, the most common trigraph is THE, which occurs a rather amazing 2% of the time, give or take, which is about 350 times the average. The frequencies drop off so quickly that any trigraph that appears even just 3 times in a 250 character ciphertext is highly likely to be either THE, AND, or ING, with the next most likely contenders being ENT or ION. While all but 4 to 6 individual characters have frequencies of about 1% or more, there are only 16 digraphs that achieve that level, and only 1 trigraph, THE, with a couple of close contenders. There aren't any 4 or 5 character sequences that we would expect to see repeated in our 250 character ciphertext, but notice that the most frequent are extensions of the more frequent trigraphs, which might allow us to make some guesses at their neighboring characters. Certainly we could go into significantly greater depth, but in the interest of time, let's rein ourselves in and focus on the 676 digraphs. Some of these are quite common, such as TH, which accounts for somewhere around 1.5 to 3% of all digraphs, or about 10 to 20 times more frequent than the average. So we would expect to see roughly 4 to 8 occurrences in our 250 character ciphertext. But there are a few others, such as HE, IN, and ER, that are almost as prevalent. Noting that T is one of our most frequently used letters, while H is much closer to the middle of the pack, if we examine the most frequently occurring digraphs in our ciphertext and one of them exhibits this trait, we have quite likely identified both T and H. Similarly, a moderately frequent letter followed by a quite frequent letter is more likely to be HE. Then there are sequences such as QU. We know that in English the letter Q is almost always followed by U. The letters Q, Z, J, and X are all at about the same frequency. In addition, they are sufficiently rare so that their rates in a short piece of ciphertext will likely deviate significantly from that expected. But if we have enough ciphertext and can identify that one of our least frequently occurring characters is always followed by a specific other symbol, it is quite reasonable to suspect that the first character is Q and the second is U, which might help distinguish U from C or other nearby letters. We can leverage the least frequently used ones to an even greater degree. There are several letters that are seldom followed by other than a few letters. We've already seen Q, which is virtually never followed by anything other than U, but other letters such as J and Z are seldom followed by any letter other than a vowel, while other letters are commonly followed by most any other letter. Not only can we use this trait to help identify the mappings, but once we have identified these letters, then any place they are followed by anything other than that small set that normally follows them, we can suspect that we found the space between two words. Finding word breaks can be a bit challenging at times, particularly if we have only mapped a few of the characters and have likely made some mistakes. So anything we can do to help identify breaks can be a significant help. This is where the other end of the frequency spectrum can be leveraged, since we have many digraphs that virtually never appear in plain text, and when they do, it is usually the result of the first character being the end of one word and the second being the beginning of the next, something that can be useful in identifying word breaks in the partially recovered plain text. Another thing that can help here is that individual letters vary significantly in their likelihood of appearing as the first or the last letter of a word. Since more than half of all words end in one of just 4 letters, we can scan our partial plain text for these 4 letters and see if a word ending in each one is readily apparent. Now let's narrow our focus even tighter on the 26 digraphs that consist of repeated characters, known as double-letter digraphs. Interestingly, I've been unable to find a list of the actual frequencies for all of the double-letter sequences, although I found numerous websites that list the top 10 or so most common in order, but only one of those had the actual frequencies. So I decided to build my own. I went to the same website that I got Moby Dick from, which archives books and documents in ASCII form, and downloaded 30 of the largest files, providing a total of over 35 million characters from sources including fiction, nonfiction, religious, literature, scientific, historical, reference, and government documents. I then wrote a simple little program to scan them and produce this table. Notice that it matches quite closely the earlier table for single letter frequencies, and so there is good reason to believe that it represents reasonable values for the double letter frequencies as well. Perhaps somewhat surprisingly, the frequency distribution of these double letter digraphs is significantly different than for their appearances as single characters. For instance, the most common double letter digraph is usually LL, which is very near the middle of the single letter frequency distribution. The next most common are EE, SS, and TT. While E and T are right at the top of the single letter frequency list, S is noticeably less frequent than either. And then we have the letter A, which is by itself quite frequent, but the digraph AA is actually rather rare, accounting for only about 1% of the repeated digraphs. We can use both the single letter and double letter frequencies at the same time by plotting our 26 letters on a 2-dimensional plot with the single letter frequency on one axis and the double letter frequency on the other. We do this for both sets of letters, the plain text and the ciphertext languages. This will frequently allow us to make very good guesses for a significant fraction of our letters. By fairly common convention, when we need to mix the two, we use uppercase letters for the ciphertext and lowercase letters for the plain text. Notice that we have a bunch of low-frequency letters crammed down near the origin. By expanding the scale, we can see that the double-letter frequencies can help out quite a bit here too, although we usually need at least 1,000 characters of ciphertext to start discriminating most of these. We'll end this lesson here, and in the next lesson we'll consider a couple of examples of using simple frequency analysis and see the impact that having sufficient ciphertext to work with can have.